Welcome to the Deep Dive, where we extract the most important nuggets of knowledge from the latest research.
Just think for a second about how your brain handles complex stuff, like following a conversation or a piece of music, or even just watching a scene unfold.
Right, you're constantly connecting what just happened with what's happening now,
Yeah.
almost effortlessly, adapting on the fly.
Exactly. And that ability, holding on to insights from way back while still processing the present, well, that's a massive hurdle for artificial intelligence. How do machines do that?
Mm-hmm. How do they mimic that sequential processing, that memory?
So today, we're doing a deep dive into exactly that quest. We're going to trace the evolution of AI models built for sequences, started with the early days, recurrent neural networks or RNNs.
And moving through the big shakeup with transformers.
Yeah, and then into this sort of surprising comeback of recurrent ideas, but in new shapes, like state space models. Our mission really is to unpack that whole journey, the breakthroughs, the unexpected roadblocks, and what's coming next where these different ideas are actually starting to blend together.
We want to understand how these models learn, what makes them tick, and why figuring out their strengths and weaknesses is just crucial for the next wave of AI.
Absolutely.
Okay, so let's kick things off right at the beginning. Recurrent neural networks, RNNs. The original vision was pretty elegant, wasn't it? Trying to mimic how we think.
It really was. The core idea was processing information one step at a time, building up this internal memory or state, using feedback loops. So the past influences the present processing.
It felt like the natural way to go. Teach a machine, like we learned, kind of accumulating knowledge over time.
And theoretically, they were incredibly powerful. I mean, RNNs were proven to be universal Turing machines.
Right.
Basically, they could, in theory, compute anything computable. And they were universal approximators, too, meaning they could mimic any dynamic system. For the early AI folks, this was huge. It seemed like the key to understanding language, speech, anything where order matters.
The dream ticket for sequential data. But like often happens, theory met reality, right?
Yeah.
And there were some big problems.
Oh, yeah. The first major one was this thing called vanishing gradients.
Vanishing gradients sounds problematic.
It was. Think of it like a message getting garbled in a long game of telephone. The signal, the information from the early steps in a sequence, just got weaker and weaker as it propagated forward through time.
So the network couldn't really learn connections between things that happened far apart.
Exactly. It struggled to remember information from more than, say, a few thousand steps back. True long-term dependencies were just out of reach for basic RNNs.
And that wasn't the only issue, was it? There's a computational problem, too.
Right. Training them usually involves something called backpropagation through time, or BPTT. And BPTT, well, it required storing all the intermediate calculations across the entire sequence just to update the network's weights.
Wow, okay. So the longer the sequence, the more memory you needed.
Precisely. The memory cost scaled linearly with length. Oh, and worse, it fundamentally lacked parallelism. You had to process step by step, which is slow on modern chips designed for parallel work.
So they tried to fix the forgetting problem, right, with things like LSTMs.
Yeah, long short-term memories. LSTMs were a clever fix. They introduced these gating mechanisms, little internal switches, basically.
Like deciding what to remember and what to forget.
Exactly. Gates to control the flow of information, letting the network selectively retain or discard things. It definitely helped mitigate the vanishing gradient problem and improve things quite a bit.
But still not perfect.
Still not perfect. Even LSTMs, while better, hit computational walls and memory limits with really, really long sequences. Thousands of steps, maybe, but pushing beyond that was tough. The core sequential bottleneck was still there.
Okay, so RNNs had this elegant biological inspiration, but struggled with long memory and speed. And then, bam, something totally different arrived.
Yeah, then came the Transformer in 2017, a complete paradigm shift. It threw out the step-by-step processing entirely. The famous paper title says it all. Attention is all you need.
Attention. How did that change things so dramatically?
Well, the key was the self-attention mechanism. Instead of processing sequentially, transformers could look at the entire sequence all at once, in parallel.
No more waiting.
No more waiting. Attention allows the model to directly weigh the importance of any token relative to any other token in the sequence, no matter how far apart they are.
Ah, So it could create direct connections between, say, the first word and the last word of a long sentence.
Exactly. It could capture both local relationships and really long-range dependencies simultaneously. And because it wasn't relying on this sequential state passing, the vanishing gradient problem, gone.
That sounds like a massive leap. Parallel processing, handling long distances.
It was huge. It revolutionized fields like natural language processing. But of course, every revolution brings new challenges.
There's always a catch, isn't there? What was the transformer's bottleneck?
Quadratic complexity, that self-attention mechanism where every token attends to every other token. Its computational and memory cost doesn't just grow with sequence length, it grows quadratically, OL squared.
Okay, L squared.
Yeah.
So double the sequence length.
Quadruple the computation and memory needed. It skyrockets really fast. So for very, very long sequences, think millions of tokens, standard transformers become prohibitively expensive.
Right, and even when just using a trained transformer, like for generating text.
Yeah, during inference, especially auto-regressive generation where you produce one token at a time, you build up this thing called the KV cache, the key value cache.
The AI's scratch pad memory.
Kind of, yeah. It stores computations from previous steps to speed things up. But this cache grows linearly with the sequence length. So again, for very long outputs, it consumes a ton of memory, which is a problem, especially for devices without massive resources.
So this quadratic cost and the KD cache issue basically created a new kind of long sequence problem for transformers.
Exactly. And that kicked off a whole new wave of research. How do we make transformers scale better? How do we get that attention power without the crippling quadratic cost?
So we had RNNs, efficient inference, but flawed memory and parallelism. And transformers, great long-range context, parallel training, but this OL2 scaling issue, it feels like a collision course.
It really did. And what often happens in science when you have two powerful but imperfect ideas, people start trying to combine them. A sort of marriage of concepts began.
Making the best of both worlds, injecting some recurrence back into the transformer.
Precisely. The goal was to gain the efficiency and maybe the inductive bias of recurrence while keeping the strong learning abilities of attention.
So how did they do that? What were some of the first steps?
One major direction was developing linear transformers. The idea was to approximate that full, expensive attention mechanism with something simpler, something that scaled linearly. OL magic. Hey, not quite magic, but clever math, often using kernel functions. Think of it like finding a smart shortcut to estimate the attention scores without calculating every single pairwise interaction.
And that made them behave more like RNNs again.
In a way, yes. Many of these linear attention models naturally operate in a stateful, recurrent manner. They maintain and update an internal state or memory matrix over time, aggregating information step by step, much like an RNN's hidden state, but often trainable in parallel.
Interesting. Does this connect to older ideas?
Absolutely. It echoes concepts like fast-wait programmers, where one network dynamically updates the connections of another. In these linear transformers, the state acts like that dynamically updated memory. You write information by aggregating key-value pairs, and you retrieve information using the query.
And we saw specific models emerge from this, right?
Yeah.
Like RWKV.
Yeah, RWKV receptance-weighted key-value became quite influential. It explicitly uses things like exponential decay to downweight older information. Plus, it has these critical gating mechanisms like receptance gates, which act a bit like the forget gates in LSTMs. It's very much an RNN transformer hybrid.
It's fascinating how those gating ideas just keep proving their worth.
They really do. And recurrence didn't just come back at the token level. We also saw it applied at a corsal level.
Like with Transformer XL.
Exactly. Transformer XL introduced segment-level recurrence. Instead of trying to process one giant sequence, it processes it in chunks or segments.
And it remembers stuff from the previous chunk.
Yes, it caches the hidden states from the previous segment and feeds them into the processing of the current segment. This allows information to flow across segment boundaries, effectively extending the context length way beyond a single fixed window.
So recurrence is back, both inside the attention mechanism and at a higher level, managing longer contexts. And gates are everywhere.
Pretty much. Gating mechanisms inspired by LSTMs became central again in many of these new architectures, controlling the flow of information. It's a recurring theme, pun intended.
Okay, so while transformers were getting infused with recurrence, another completely different approach was also gathering steam. State space models, or SSMs.
Right. SSMs come from a different background, often control theory and continuous time systems. They offer another really efficient way to handle sequential memory.
How do they think about memory differently?
At their core, you can think of SSMs as highly efficient information compressors. Their theoretical grounding, particularly from work like Hipio,
Hippo, like
uh,
the animal.
yeah, but it stands for high-order polynomial projection operator. Hipio theory provides a mathematical way to optimally compress a continuous input history into a compact state representation. It finds the best low-dimensional projection to summarize the past.
So instead of trying to remember everything like attention or feeding like RNNs, it intelligently summarizes.
That's a good way to put it. It keeps a compressed but high-fidelity memory of the important dynamics of the sequence history.
And how did this translate into practical models? We heard names like S4.
Yeah, S4 and its variants were major breakthroughs. They took these continuous time SSM ideas and discretized them into very efficient linear recurrences. They use special mathematical structures for their state matrices, often diagonal or near diagonal, which unlocks huge computational savings.
What kind of savings?
This is the really cool part. Models like S4 can be trained in parallel, much like a convolutional network or a transformer. But during inference, when generating step by step, they operate as an RNN with constant memory and computation per step. O1, complexity for autoregressive generation.
Oh, one. So the memory needed doesn't grow at all as you generate longer sequences.
Exactly. That's a massive advantage over the transformer's growing KV cache, especially for very long outputs or on resource-constrained hardware.
But were these early SSMs good at everything? Did they have weaknesses?
Early SSMs sometimes struggled with tasks requiring very precise recall of specific information, things transformers excelled at, like copying tasks or recalling specific facts associated with keys, sometimes called induction heads.
Okay, so the compression maybe lost some specific details.
Potentially. Or the fixed linear dynamics made it hard to model those specific input-dependent lookups. But then came further innovations. H3, the Hungry Hungry Hippo model, tackled this.
Sticking with the hippo theme.
Right. H3 used multiple SSMs combined with gating mechanisms that allowed the model to compare different parts of the sequence, making it much better at associative recall tasks, almost like adding a searchable memory component.
And then, Mamba. That seems to be the name generating a lot of buzz lately.
Mamba is arguably the next big leap for SSMs. It introduced selective state spaces. This is the key innovation.
Selective, how?
Unlike previous SSMs where the state update rules were fixed, Mamba's state transition matrices depend on the input data. The model can dynamically change how it updates its state based on the current token.
Ah, so it can decide what information is important to keep or forget at each specific step, based on the context.
Exactly. It allows the SSM to selectively route information, focusing on relevant parts of the history and ignoring irrelevant parts. It effectively mimics the context-dependent selective read-write behavior of attention.
But without the quadratic cost.
Precisely. Mamba achieves that selectivity while maintaining linear time complexity, OL, for training, and crucially that O1 constant memory for inference. It brought context awareness to the efficiency of SSMs.
That sounds incredibly promising. Are there other related ideas popping up too?
Definitely. We're seeing things like Hyena, which uses very long convolutions combined with gating, achieving similar efficiency goals. And XLSTM is trying to modernize the original LSTM with matrix memories and better parallelization. The whole space is incredibly active.
Okay, wow. So we have souped-up RNNs like RWKV, transformers getting linear approximations and recurrence, and these super-efficient SSMs like Mamba learning to be selective. How on earth do we compare them? Which one is best?
The million-dollar question. And it's tricky because best depends heavily on the task, the sequence length, and the constraints like memory or latency. Plus, the definition of a long sequence itself keeps changing. It used to be hundreds, and now people talk about millions of tokens.
So we need good benchmarks.
Absolutely. And researchers have developed specific tests. One classic is the copy task, just simple memorization. Can the model reproduce a sequence it saw earlier?
How do they fare there?
Interestingly, this is where some transformers, especially ones with modifications like hard alibi, show a real edge in data efficiency and what's called length generalization.
Meaning they learn faster and work on sequences longer than they trained on?
Yes. They often need fewer examples to learn the task and can successfully copy sequences much longer than anything seen during training, while some SSM variants can really struggle or even collapse to random guessing on longer unseen lengths. It shows the raw power of attention for certain memorization patterns.
Okay, but what about more complex memory, like finding patterns or associations, induction heads, or associative recall?
Right. Those tasks test if a model can learn rules, like if you see token A, then later expect token B. Basic linear SSMs could struggle here too. But the more advanced ones, like H3 and particularly Mamba, with their gating and selective
You
states,
can match transformers.
they often can, yes. Their selective mechanisms allow them to effectively store and retrieve specific pieces of information based on the content, acting like efficient differentiable lookup tables.
Got it. And what about broader benchmarks like the Long Range Arena, LRA?
LRA is a great suite. It tests models on diverse tasks, list operations, text classification, images, even pathfinding puzzles, all with very long sequences, up to around 16,000 tokens.
And who wins there?
Often, it's the hybrid models that do really well. A model called Mega, for instance, which combines transformer-style attention with an efficient SSM like kernel, frequently tops the LRA leaderboards. It suggests combining strengths is powerful.
But if you push the length even further, or speed is absolutely critical.
That's where pure SSMs really shine. For tasks with extremely long sequences, like the 16K PathX task in LRA, or situations demanding very low latency during generation, models like S5 or even simpler ones like LRU can provide very competitive accuracy, but with that guaranteed linear scaling and constant time inference. That's a huge practical advantage over standard transformers in those specific scenarios.
So summarizing the trade-offs for someone building an AI. If you need rich, complex interactions across the whole sequence in memory isn't your absolute tightest constraint, transformers are often great learners.
Right. But if you're dealing with truly massive sequences, like million token contexts, or if you absolutely need that O1 inference efficiency, say for on-device applications, then modern SSMs, especially selective ones like Mamba, look increasingly attractive.
It sounds like there isn't one perfect model yet. The future seems to be about mixing and matching, hybrid approaches.
That definitely seems to be the direction the field is heading. No single silver bullet. We're seeing more and more blended architectures. Models like Griffin, for example, which intersperses SSM layers with blocks of local attention that only looks at a nearby window, or Jamba, which explicitly mixes transformer and Mamba blocks, often using a mixture of experts' approach to activate different parts of the model depending on the input.
Trying to get the best of both.
Yeah.
The transformer's learning ability and the SSM's efficiency.
Exactly. Some studies are even trying to figure out the optimal mix, suggesting maybe something like a quarter attention layers and three-quarters SSM layers might be a sweet spot. It's an active area of research.
And beyond just the model architecture, there's also the hardware side of things, right?
Yeah.
You mentioned efficiency isn't just about counting operations, the FLOPs.
That's a crucial point that's become much clearer recently. Reducing the theoretical number of computations, the FLOPs, doesn't automatically mean faster real-world speed, the wall clock time. Because the real bottleneck on modern hardware like GPUs is often memory access. Moving data between the super fast, small on-chip memory, SRAM, and the larger but much slower main memory, HBM, takes a lot of time and energy.
So even if an algorithm does fewer calculations, if it constantly needs to fetch data from the slow memory, it can still be slow overall.
Precisely. This has led to innovations focused on hardware-aware efficiency. Things like flash attention.
Flash attention. Sounds fast.
It is. It doesn't change the quadratic nature of attention, but it cleverly reorganizes the computation using techniques like tiling to drastically reduce the number of times data needs to be read from and written back to that slow HBM.
So it makes quadratic attention much faster in practice, even if the OL2 scaling is still there theoretically.
Exactly. And similar ideas like flash linear attention are being applied to make linear attention methods even more efficient, too. It's about optimizing the whole stack, from the algorithm down to the metal.
This whole journey is incredible, but it feels like we're still mostly talking about processing really long but ultimately finite sequences. What about the truly grand challenge, the human-like ability to learn continuously?
Ah, yes. The frontier. Moving beyond just long sequences to tackling potentially infinite-length sequences and achieving true lifelong online learning.
That sounds like a whole different ballgame.
It really is. Think about the fundamental disconnect. Most AI today is trained on massive but curated and finite data sets. You train it, you deploy it, maybe you fine-tune it later on another data set.
But that's not how we learn, is it?
Not at all. We learn from a continuous, unsegmented fire hose of sensory input sites, sounds, language our entire lives. We don't get neat batches or manual resets. We just keep learning.
That original dream of the RNN pioneers you mentioned. They were thinking about this.
They absolutely were. The aspiration was for online algorithm systems that could learn while they operate, continuously adapting to new data without needing someone to manually reset their state or segment the input, and crucially, without needing to store an infinitely growing history of past computations.
That sounds incredibly difficult.
It's a monumental challenge. It requires rethinking not just the models, but the learning algorithms themselves, and even how we evaluate success. How do you measure performance for a system that's supposed to learn and adapt forever? It's still largely an open frontier.
What an amazing arc we've covered. From RNNs trying to mimic thought but hitting walls,
Yeah.
to transformers breaking through with attention but facing scaling limits, and now SSMs offering incredible efficiency and selectivity, with hybrids blurring all the lines.
It's clear the boundaries are dissolving. Each paradigm is borrowing strengths from the others. Recurrence is back in transformers. Selectivity is boosting SSMs. Attention is being made more efficient.
And for you listening, thinking about this evolution isn't just about the technical nitty-gritty. It's fundamental to how AI will learn and reason in the future. How will machines handle the endless stream of information the real world throws at them?
Getting closer to that fluid, continuous learning we take for granted is the key.
So the provocative thought to leave you with is this. What truly becomes possible when AI can learn continuously, without forgetting, adapting moment by moment to an unending flow of data? What new kinds of intelligence might emerge when we move from just long sequences to truly lifelong learning?
That's the horizon we're heading towards, an exciting and perhaps slightly daunting future for AI.